Okay, so let's continue. Now this is a little different because we can see that we've got e to the 2x in two different places. So again, how do you decide which one? Well, if I have something in my denominator, then chances are I'm going to make that my u value because there are very few derivative properties where we ended up with something or putting something in our denominator when we take the derivative. So it's going to be best to let that be our u value. So let's let u equal 1 plus 2x, or rather 1 plus e to the 2x. And then it follows that du is equal to 2e to the 2x, right? The derivative of 1 is 0. Here we do e to the 2x times the derivative of 2x, which is 2. So we get 2e to the 2x dx. Okay, so that said, this works out pretty simply for us. We are integrating. If I go ahead and plug in 0, e to the 2 times 0 is going to give us 1. So our new lower limit is 2. And if we put in 3, we get 1 plus e to the 6x, or rather 1 plus e to the 6. All right, and I'm going to leave it just like that because I don't want to do any rounding at this point, okay? And we can look at this as du over u. All right, because we have du up top, all right, and then we've got our u on the bottom. So we know this integrates as natural log. All right, it's going to be the natural log of u evaluated from 2 to 1 plus e to the 6, or we get natural log of 1 plus e to the 6 minus natural log of 2. All right, and you could put that in your calculator. Don't forget that typically we do absolute value bars when we do natural log as the solution of an integral. But if you know that this thing is not negative or can't be negative, then it's okay. And of course, e to the 6 plus 1 is not negative. Neither is obviously 2. All right, let's look at C. All right, so we got the integral from 1 to 3 of e to the 3 over x. Actually, I think we just did this one. Yes. So let's look at e. All right, we're looking at the integral from 0 to 1 of x times 5 to the x squared dx. Okay, so this is a great one for u substitution. I see some parts and pieces. We have an idea about how we want to integrate basically a to the x, or a to the x, a to the u. So we just got to make sure we've got everything in place, and that's why we're going to do this u substitution. So we got u equals x squared. All right, I'm going to choose that because it's algebraic, and I can already kind of see that the derivative of x squared, or at least a multiple of that, is present. So we get du is equal to 2x dx. All right, and so what we have is x dx. So I need to solve for that. We can say du over 2 is equal to x dx. All right, so I can rewrite this then as the integral from or of 5 to the u, and then I'm going to do a 1/2 outside of my integral du, okay, for my x dx. All right, so if you go back and look at the rule for a to the u, okay, the integral of a to the u du is equal to a to the u over the natural log of a plus c. All right, so we've got everything in place already. So this is going to be 1/2 times a to the u over the natural log of 5, okay? All right, if we go back and look at our limits, we had 0, and so we're still going to have 0, because 0 squared is 0, and then we're still going to have 1, because 1 squared is 1. So we're going to evaluate this from 0 to 1, and that gives us 1/2 of 5 over natural log of 5 minus 5 to the 0 is 1, so 1 over natural log of 5. All right, so for E, this would be our final answer. Of course, we can simplify 5 minus 1 and get 4 natural log of 5. And then, of course, we can cancel the 4 with the 2. And so we would end up with 2 over natural log of 5 is our final answer. All right, let's look at F. Here we've got the integral from 0 to pi of e to the cosine x sine x dx. This one looks pretty straightforward. Okay, in this one, I'm going to let u equal cosine x and du equals negative sine x dx. All right, so that means negative du is equal to sine x dx. All right, so when I rewrite this, we're going to get the integral of, well, we're going to put our negative on the outside. We've got e to the u du. Okay, our new limits of integration, we can do cosine of 0. Well, that's going to be 1. And cosine of pi is negative 1. So, of course, we're going to flip that around and get positive the integral from negative 1 to 1 of e to the u du. And so we get e to the u. We're going to evaluate that from negative 1 to 1. So that gives us e to the 1 minus one over e. Okay, now let's revisit completing the square. And so here we have this problem dx, or the integral of dx over x squared plus 12x plus 37. And when we look at it, you know, the only choice really for u would be what we have here in the denominator. But we can see that we don't have that derivative present anywhere. Okay, so in this case, we might shoot for completing the square so that we have a sum or difference of squares, and then perhaps we can use one of our inverse trig functions to get to the answer. So let's complete the square. I'll do it over here. If we complete the square, we get x squared. We're going to start with x squared plus 12x plus 37. And to complete the square, we take half of this middle coefficient and we square it. So that looks like x squared plus 12x. I'm going to add in half of the middle coefficient and square it. So that's going to be plus 36. Okay, half of 12 is 6. It's squared is 36. Okay, plus 37 minus 36, because we can't just throw a 36 in there. We've got to compensate for it. So we added it, we subtracted it. There's no net change. All right, so I can go ahead and factor this now. I forced it to be a perfect square. This factors as x plus 6 squared plus 1. All right, and if you recall, this looks like our formula for tangent inverse. It was the sum of squares. All right, so we still need to make sure we've got the right u substitution and we got all of our parts and pieces in place. So in this case, we're going to let u equal x plus 6. And du equals dx. Okay, so this is the integral of dx, or if we rewrite it in terms of u and du, we've got du over u squared, right? This is our equivalent expression for what we had in the denominator. And it's probably a good idea. We don't like to skip too many steps in our work. So let me do this. Okay, we're going to rewrite this as the integral of dx over x plus 6 squared plus 1. Okay, and now I'll write the integral of du over u squared plus 1, which 1, of course, is already a perfect square. And so we can think of that as tangent inverse of x plus 6 plus c. All right, let's see what it looks like if we try something similar on B. And I think someone asked a question about this, like what do we do if we've got a negative there? So we're going to work it out. Okay, the first thing I'm going to do, whenever we complete the square, it's important that the coefficient on the squared term be positive 1. Okay, so we've got a negative 1 there. So let's go ahead and fix that. We can rewrite this as, first of all, we got 4x minus x squared. I'm going to rewrite it as negative x squared minus 4x. Okay, so I've just factored out the negative. All right, and I can complete the square, right? This is going to be minus x squared, okay, minus 4x. I take half of that coefficient and square it. So that's plus 2 squared. Okay. However, even though we said plus right here, we have to remember that that's going to be impacted by this minus sign that's outside of parentheses. So really, instead of just adding 4, what we did was subtract 4. And so to compensate, I'm going to add 4 over here. Okay, this was minus 4. And so to compensate, we say plus 4. And so this gives me negative x minus 2 squared plus 4. Or we can write this as 4 minus x minus 2 squared. Alrighty. And so we can think of our a as 4, or actually a is going to be 2, and u is x minus 2, and du is just going to be dx. Okay, du equals dx. All right, so when we try to put all of this together, okay, we can rewrite this as the integral of dx over the square root of 4 minus x minus 2 squared. All right, and so we found that du was equal to dx based on our definitions. So we got the integral of du over the square root of a squared minus u squared. All right, and so if you look back at the formulas, we see that this is the pattern for sine inverse. And so we get sine inverse of, it would be u over a. So that's going to be x minus 2 over 2 plus c.